Actually, okay. Okay. Good afternoon and welcome to our weekly seminar. My pleasure today to introduce Dr. Auroop Ganguly from Oak Ridge National Labs, where he's in the Computational Science and Engineering division. Auroop has his PhD in Civil and Environmental Engineering from MIT. 5 years ago already. 2002, time flies. And his recent work has been in understanding climate variability and its influence on its local impact. So without further ado, Auroop, the floor is yours.
Thank you very much. And I'm going to talk about a couple of things. Quickly, I'm going to introduce the topic of what we call knowledge discovery. It's just the quote-unquote new kind is just is sort of meant half in jest. So, and also then focus a little bit on a case study on climate change, specifically focusing on climate extremes and uncertainty, which has been the focus of my research. ornl.gov/knowledge discovery is and /climate extremes is where you'll be able to find more information. So broadly, what we mean by this knowledge discovery is offline predictive analysis combined with online decision making, and we define offline predictive analysis in this context to include pattern detection, broadly construed from very large data sets, as well as process modeling in the context of or in situations where we have large data sets, but also in situations where the data sets may not be large enough and we have some conceptual understanding but not enough in some cases to be able to have very well defined physics. So we may have well defined physics, we may not have, but combining all of these could take the form of data guided or computational data sciences. This could take the form of data guided model development and feedback between them, which leads to a body of actionable knowledge. And when we get a stream of new data that contributes both to the data that is stored, leads to the body of actionable knowledge and leads to decision based on whatever insights we already have from the offline predictive analysis. So, and the focus here is on rare events, uncertainties, and impacts of these rare events. Just to give a little bit of context, this was done in collaboration with some with various professors as part of defining the knowledge discovery agenda for the lab and especially for our division. So that's why it has a slightly broader feel about this. And in general, what this means is there are broadly three pillars, if you will, to this knowledge discovery. One is interdisciplinary blend of tool sets spanning the computational data sciences with a focus on rare events and change. So going beyond traditional data mining to situations where you're more interested in understanding extremes, interested in understanding change, abrupt change, and our uncertainties with those. Process models, which would deal in this context with situations where the physics may be somewhat well known to not very well known, but you have to infer this from data. So understanding things like emergence or the ability of models to provide surprising behavior versus predictability and systematic evaluation of model strengths and limitations, leading to uncertainty characterization as well as uncertainty reduction where this is possible, and hopefully some guidance for policymakers. So in terms of interdisciplinary data and computational sciences, which has been one of the focus, my research has touched upon all of these areas, and this division into data sciences versus computational sciences is completely arbitrary. But things like time series and spatial statistics and nonlinear dynamics all the way to spatial and spatiotemporal data mining. Community is gradually forming in areas like data stream mining. Some of us and our collaborators, we have been working with communities like ACM and IEEE and others to start to develop some traction in this case in the area of data stream mining. I've done some work in nonlinear dynamics, specifically focusing on what happens not in situations where experiments are relatively easily repeatable, or where we have data which are relatively free of noise or high frequency variability, but in situations which we, for example, encounter in areas like geophysics and elsewhere, where we have the data sets that we have. So we are stuck with sometimes short data, and short in this context means short compared to what you need, short in terms of something that spans the nonlinear dynamical attractor with enough sampling frequency. So in that context, a lot of the data sets that we have is short and potentially noisy, and this noise may not usually be white noise in these situations. So just to give you a quick idea of some of the work we have done earlier is trying to look at detectability of nonlinear determinism or chaos from systems which are contaminated with noise and seasonality, starting with simulated systems and going to real observations in hydraulic systems hydrologic systems, and then looking at dependence structures. So going from linear correlation to monotonically increasing, for example, rank-based correlations like Kendall's tau 2, going to things that are, for example, based on mutual information, which could capture the full dependence structure in principle, but which typically have issues when we start to think about short and noisy data sets. So the question then is, what is the best we can do when we are stuck with short and noisy data sets, and what are the various recipes that we can use for estimating mutual information, how good they are. So and then applying these to a geophysical problem where we look at El Nino index and river flows across the world, and trying to say that whether there is some additional dependence over and above what linear correlation like measures or measures like cross coherency on the kind of approaches can provide. So that's one line of work. We've also done some work in the area of characterization and assessment of extreme events in space and time. And what I mean by these are things like 100-year return level, things that happen or happen in a probabilistic sense once every 100 years, and how these might change over space and time. So are there any spatial patterns? And for example, if we are talking about 100-year rainfall events and we are thinking about climate change, then are these 100-year rainfall events, which is best interpreted as 1% probability of let's say this high intense rainfall happening, are these 100-year return levels changing in terms of their statistical attributes? And if there is a change, how much is that changing? So if we have, as civil engineers, if we have designed infrastructures, which we do, based on 100-year return levels, and if those things change, then how much are they changing? So if it changes, and that is an important characteristic to measure in over space and time, because if it changes significantly so that it's higher than the design factors that we have incorporated in our infrastructural design, then something needs to happen. Either those infrastructures have a chance of breaking now, or we need to either reinforce them or do something with them. So that's one thing. The the other areas that we have looked at is dependence between these extremes. So tail dependence, which is saying that are 100-year events between variables or 100-year events in space-time related to each other. Why is that important? Well, if we have 200-year events that are happening in two different locations and they are completely dependent on each other, then these 200-year events still represent a 100-year event taken together. But if they are completely independent, then it becomes a 10,000-year event. So that gives us a way to understand both dependence patterns and detect change, for example, in the context of climate. Yeah.
So you use copula-based methods to determine
tail dependence.
And what was your conclusion? Is there strong dependence?
So we looked at observed data sets from rain gauges, compared that with climate portal simulations. In terms of general patterns, we saw that, in space-time, we saw that the patterns look similar visually, but then when you look at them quantitatively as to the extent and that there are discrepancies. That's what we found. So those are just few examples of the interdisciplinary data sciences that we have addressed, and I'm going to talk more when we go to the case study. But what this also means is that these kind of tools, broadly what we are calling knowledge discovery, lets us target multidisciplinary societal priorities. So in terms of sustainability sciences, some of the work we have done touches climate change, water resources, environmental monitoring based on sensors, energy assurance. And in national security kind of applications, we have looked at transportation hazards, social economic behavior, population uncertainty. I'll talk a little bit about some of these, and infrastructure risk, which I'll not talk about here, but which was a fairly interesting work done for the Department of Homeland Security Office of Infrastructure Protection, where they wanted us to look at risks in a fairly comprehensive way by looking at each component, likelihoods, vulnerabilities, and consequence base for different types of hazards, man-made hazards and natural hazards. So here is one example of the kind of applications that we have worked with and the tools we have developed. This was for a problem in transportation security, where we have, probably all of you have seen weigh stations on the interstates. So what this says is that commercial vehicles are intercepted and investigated at the weigh stations anyway. So can we place sensors in those weigh stations, sensors very broadly defined, from radiation sensors to static scale weights to different types of cameras, video, etc. Can we place different types of sensors and start to monitor these and broadly come up with a multivariate characterization of each truck? And once again, this is a very broad generalization, but come up with a multivariate characterization of this truck based on this heterogeneous multimodal data. And then when one new truck comes in, we say that yes, this is a security hazard or not with this kind of, with this much likelihood. And that helps in decision making. The thing here is though, is that we do not have enough trucks. Sometimes we don't have any trucks that represent security hazard. Security hazard in this case means, for example, trucks that carry materials for dirty bombs. So we do not really have the imbalanced class. We do not really have trucks of the rare class. The idea is to get better and better at predicting what is usual, when we miss them, and when they go to decision makers, we know why these things were missed. So even though this anomaly was picked up by this data system, the user says this is not an anomaly because of this reason. So that becomes something that adds on to our reason codes, if you will. So we get better at modeling the usual, and then we say this is something that represents the unusual. Yes. So
do you use things like hidden Markov models to describe the behavior and then detect anomalies, or
yeah,
statistical objects?
In this case, the kind of tools that we use based on the kind of data sets that we have, for example, In the case of static scale weights, we used anomaly analysis based on a variety of nonlinear dimensionality reduction approaches, isomap and LLE kind of approaches. In the case of spectroscopy data, we used a variety of time series approaches combined with finding things that are that fall within certain usual bands versus that don't. So we have a variety of approaches tailored towards each of these sensors, and then something that talks about the whole track. So it's a combination of many different approaches. One thing we have not done in this particular case, just because we did not have enough data when we started, and that slipped a little bit in the list of priorities, is go towards behavior modeling too much. We are not able to do that. So that is something that needs to be explored at some point. We looked at online detection of anomalies, change and change point from space-time data, specifically remote sensing type of data, and in different ways. In this case, for example, we are looking at NDVI, which is a measure of greenness, and then using Walmart store opening. We had many different data points about Walmart, so using Walmart store opening as validation points, because once you have one Walmart store, it sort of spreads chaos to the vegetation around slowly, and trying to use that as a validation point to see if we could detect the change and then go back in time to detect change point and see when that Walmart store opening actually happened. Yeah. These pictures represent the NDVI indices. These are Walmart stores. So this is one individual, the region around one Walmart store, and what we have here, the green is the usual the vegetation at a point which is far enough from Walmart store but close enough so that it's the same type of vegetation. Blue is bordering area, red is the area in or around Walmart. So we do see visually, when we see this, we do see these things growing apart gradually. Question is how best can we detect the change when, and can we go back and detect the change point? How good are we at that?
Sorry, I couldn't read the time scale. What's the periodicity? Is it an annual cycle we're looking at?
This is an annual cycle, yes. The other, and we have more details on each of these. For some of these things, there's a one slide approach to a whole bunch of things that was done, but I have some references listed here which has some more details on this. And I'll zero in on only one case study, which I've been increasingly focusing on now. So one other area that we have looked at is systematic evaluation of social science theories and models. This was a DARPA-funded project which involved ORNL and some university partners. My task mainly, or the task that I was leading, focused on evaluation, which eventually became one of the motivating themes for this application. Is basically what DARPA was interested in is trying to find how good these models are at producing surprising behavior and at predicting something. Everybody knows that in these kind of models, the state of the art does not allow you to predict one specific thing, but can you at least predict broad behavioral patterns at some point? How good or bad are we? And there are some examples which lets us do that. So we carried out a fairly detailed study based on a variety of tools ranging from nonlinear dynamical methods to certain approaches specific to this domain to see how good some of these models were. So broadly, an evaluation of complex models. There is some sort of community interest building up in this area. There was one workshop organized by Roger earlier, which I would put broadly in this category, in the area of uncertainty. There was recently there was a next generation data mining conference organized with NSF funding as well. NASA has been organizing a conference on intelligent data understanding for the last 3-4 years now, and they are building it up more and more. We have been organizing some conferences in ACM, the Computer Science Society, and IEEE in areas like sensor-based knowledge discovery, climate data mining, and in AGU and AMS in nonlinear dynamics and extremes. So now that's different types of things that we have been doing in this area. And one advantage of being in a lab is that we can afford to be fairly broad. That's also sometimes a disadvantage in terms of breadth versus depth, but that's how it is. So I mean, we have defined one broad theme in this area that we are calling knowledge discovery, as I have explained, and then within that we have targeted several example areas. Now I'll drill down into this one case study, or one very broad area in climate change. Now, broadly, the area that I have targeted really with my research is translation of climate science to decisions. What are the biggest issues there? Well, one is regional climate prediction. So before I get there, in terms of decisions, I mean decisions that are taken, for example, by water resources managers, by infrastructure managers, to understand, for example, what happens when the attributes of 100-year rainfall changes. Water resources managers, what happens when population grows, and I have some examples of that. Population grows and the precipitation reduces, for example, those kind of things, and we have looked at some specific examples of those. And also decisions at a more aggregate level, for example, the kind of decisions that need to be made by policymakers in terms of emissions regulations. So trying to inform those decisions with the best climate science we have, which implies both a focus on understanding mean and extreme processes at local, regional, and global scales, but also conveying the uncertainties. So one recent article in Nature mentioned that some of the major challenges in climate science, I mean, of the 4 real holes in climate science, that's what they called it, 2 were regional climate prediction and precipitation. Regional prediction includes extremes, and uncertainties are all part of this, and in the context of translating these to impacts, thresholds, nonlinearities, and tipping points, and feedback between systems become very important. So my research focus at ORNL has been broadly within this climate extremes area, defined to include severe events, large regional shifts, characterization of uncertainty, both in terms of predictive skill and in terms of bounding what we know from the science for decision makers, and risks, as in likelihoods, vulnerabilities, and consequence. So this figure is from the IPCC AR4, the 4th assessment report of the IPCC, which has been in the news recently for the wrong reasons. But this says that without anthropogenic emissions, we'd be in a slightly cooling trend now, globally speaking, and even for most of these continents. So what this is showing is the black line for each of these is the observed. The blue bound is the bound from many different models with just natural forcing, without human emissions. And this pink is the bound from multiple models with natural forcing and human emissions. So with human emissions, we are seeing the pattern of warming. The observed is following these patterns for a while, and then it clearly goes along with the observations. So at global to continental scales, especially for 50-year to century scale timelines, the science is pretty much solid. It's not that everything has been resolved, but a lot of these things we understand fairly well. And that is the basis of what was sent to the policymakers. However, there are issues. So this table also comes from IPCC AR4, not these things that I have added here in terms of increasing skill and increasing importance, just this table itself. And what this is saying is that if you think of temperature-related extremes, heat waves, cold spells, etc., the credibility of those assessments are larger than precipitation-related extremes, So severe storms is here, droughts even lesser credibility, and by the time you get to tropical cyclones and then to sea level rise, you have less and less credibility. However, in terms of stakeholder needs, sometimes the importance is exactly reversed. We care more about sea level rise if it completely floods my island nation. We care about hurricanes, and then we care about precipitation and heat waves. Sure, we care about those. They can have impact on diseases and so on and so forth, but potentially less than the others. So that's the situation right now in terms of extremes. Yes?
How did they, how was the decision made of calling something very likely or something that's likely? Or
In the IPCC itself? Yeah. So this was, so the whole IPCC process was synthesis and assessment of all the existing climate science that was out there before this assessment was made. So these group of scientists, their job for the IPCC is not to do new science but to do this assessment. This is based on a combination of all of those, what they found in the literature, in the peer-reviewed literature saying, okay, this we know with some confidence, this we don't, and that kind of thing. So there, and that's what this whole process is supposed to be.
Numerical correspondence?
Is that-
Likely means
Oh, there's a-
above 66%
Yeah.
of confidence. Very likely is
Nine-
about 90.
Above 90, yeah.
how do they get the assessment of something being 90% likely?
Yeah, there's a fair amount.
There's a fair amount of subjectivity, but it's based on the literature. So then you have to look at each one of them and try to understand how they got that. But I mean, they have specified how they have obtained this, right? Whether that how is quantitatively satisfying to all scientists and engineers, that is a matter of debate. But at least what this says to me is that this list, this relative ordering is probably okay. We do understand heat waves better than we understand hurricanes, for example.
Is that something that they're working on?
Yeah, I'll come to extremes is something that I'm working on, so I'll come to that.
What AR4, AR5 mean?
Oh, AR4 is the fourth assessment report of the IPCC, which was came out in assessment report, which came out in 2007. AR5 is the one that's going to come out later, the next one. So, I mean, all that this says is that the focus, because there is a need to translate the science to impacts more and more, the focus is shifting quickly to regional analysis and to decadal scales, understanding of extremes and uncertainty. So trying to evaluate models and individual processes along with their uncertainties and trying to reduce this uncertainty in some way. So for example, this is one illustration where models right now are not that good. They're not that good in terms of understanding how oceanic dynamics might influence extremes over land, and this is called teleconnections, which is a well-known climate phenomena. So we sort of understand the conceptual physics. We may not be that good or as good as we would like in terms of understanding how we can quantify this with the physics. However, now we have lots of data points from various types of remote and in situ sensors. So one question we are investigating is, can we start to use all of those data to reduce the uncertainty? So here is something that at a fairly broad brush overview of some of these uncertainties. This is temperature at decadal scales, and these are things we have, many of these are things we have published, so I can point you to more details, but broadly what this means is that when we look at models minus reanalysis or surrogative observations, let's say model minus observation, at decadal scale, we see that the errors themselves, not the actual temperature values, not the absolute values, but the errors themselves are fairly Gaussian when it comes to temperature. They are well behaved, so they can be handled as mu plus minus n sigma kind of bounds. When we look at precipitation, however, these errors are non-Gaussian, non-homogeneous, non-stationarity, both in the mean and the variance, and no one statistical error distribution fits all grades. So that immediately becomes interesting, especially in the tropical regions. This is an example where we are looking at changes in temperature using the current 30-year period from multiple models as a baseline. We were looking at what happens in the 30-year period at the end of the century. Why did we pick 30-year period? Because most of these teleconnection oceanic influences that we know matters for temperature change, they smoothen out at those kind of time scales, 30-year time scales. So we are looking at that. And then these are individual models. The plots on these figures are individual models, and this shows direction of change, how much change we expect in that 30-year period. And this is global, and then we have different continents here. For temperature, what we see is that there is some fair amount of disagreement, but they at least agree in the broad pattern in terms of the direction of the change. Precipitation, even at this global scale, and these are all global scale 30-year average, supposed to smoothen out a lot of stuff. Precipitation from these multiple models do not even agree on the sign of change. Same with latent heat flux, which relates to evaporation, and same with soil moisture. So that's an interesting aspect of the uncertainty, even at global to regional scales. Now this is looking at one of those climate models, CCSM3, Community Climate System Model, version 3, and this is looking at one simulation from those and saying what could this mean at local to regional scales. So the implications could be fairly dire. If you look here, these are changes in temperature patterns. The darker this is, the higher the change. And once again, we have more details, but this visually shows, wow, I mean, this is growing really warm, this place, and this is 2050s. So this is the average of the decade around the 2050s minus the average of the decade around the 2000s, which is now. This is getting fairly warm, and in 2100s this is getting even worse, especially if you look at western US. This is rainfall, and shades of yellow indicate drying pattern, blue indicate wetting pattern. So once again, you see that in the western US you have drying and warming happening at the same time, so there could be fairly dire situations. However, we also have to think about the uncertainties in some of these things. If we look at temperature, as I was saying, the uncertainties are relatively less, generally speaking. However, if we look at changes in precipitation, this is the average of 9 models for what is called P minus E. P minus E is precipitation minus evaporation, water that goes in and water that comes out. So it is a measure of land wetness. Delta P minus E is the change in land wetness. This is an average of 9 models. It shows that while there is drying in the western US on the whole, nothing much seems to be happening in the eastern US, southeast, other than Florida, but there is a pattern of drying here. This is NASA's GISS model, and this shows there is significant drying here, broad region, and significant wetting here. This is Japan's MIROC model, and we have results from all of these 9 models. Japan's MIROC model, and this shows drying here, but if you are thinking about local scales, the patterns are not the same. If you are thinking about broad regional patterns, they could be similar. On the other hand, here it shows drying as opposed to wetting. And if you look at population density map like this one, this is where a lot of the people happen to live. So we cannot afford to be so wrong here. So these suite of IPCC models used by IPCC for their assessment reports, were selected based on their performance. They had to pass through some basic validation criteria, but mostly at global to continental scales, at which scale some of the errors tend to cancel out and so on and so forth. But there is a lot of work to be done at regional scales, especially for precipitation. So no wonder that Nature article said that 2 of the 4 biggest holes are regional predictions and precipitation. Then there are some kinds of uncertainties which are difficult to even quantify with the set of tools that we have right now. So this is the Himalaya region, and we know that that region is getting warmer. However, the current generation of climate models do not have good ways of representing terrestrial glacier melting of land glaciers. So what this warming pattern means for this melting, that's what we don't understand that well. However, if we do not consider that, this is what the land model says, that the runoff in the rivers show a slight increase. However, if these glaciers do melt at some point in time, then what could happen is that you'll get an initial surge of runoff, and then these rivers might become more like seasonal rivers. So we just don't understand enough about this to be even able to quantify these uncertainties. But then again, these are some of the most highly populated regions in the world. So East China, this part of India, Pakistan, Bangladesh. So what we are saying here is that climate models are necessary but may not be sufficient for future projections, at least the current generation of climate models, the way they are designed right now. And there are several areas here which needs to improve. One is the statistics of severe events, regional and decadal scale projections, the oceanic indices and how these relate to land extremes or regional changes over land. The AR5 suite of models, the IPCC's models which will feed into the 5th assessment report, are supposed to be better in terms of the physics and more highly resolved, but it remains a hypothesis as to how much improvement exactly will result from them. We think there will be significant improvements, but those need to be tested. We do have a situation though right now where we have massive and disparate data from many different types of remote and in situ sensors. So the earth sciences has almost transformed from being a fairly data poor environment to a data rich environment because of remote sensing and other in situ sensor networks. So one thing we have been thinking is, can spatial and spatiotemporal data mining, and we can think of this as computational data sciences combining spatial statistics, time series statistics, nonlinear dynamics, data mining, but in the context of massive data sets. So can these come to the rescue? Well, traditional data mining approaches motivated from computer science have usually assumed IID, independent and identically distributed processes. However, in this case we know that learning samples are not independent. So the first thing is, of course, that climate data are geographical, which means that there is a proximity based correlation. Then there are several other things which means that we need to go beyond even what could be called traditional spatial and spatiotemporal data mining. There are non-stationary patterns in terms of climatic influences. So for example, how teleconnection patterns might influence regional climate over land can change within decadal time periods. Certain broad behaviors of climate have changed earlier, and this is not because of any anthropogenic cause or global warming, or potentially not because of them, just natural changes in teleconnection patterns. There are fairly complex dependence structures because the processes are nonlinear and could be even chaotic. There are low frequency noise, long range spatial dependence. So what this means is, now when we look at correlations, so in spatial and spatiotemporal data mining, the computer science community argues that we go one step beyond traditional data mining because we consider correlations over space and time. Things that are closer are usually related more to each other. However, here we are not only looking at that, but you're looking at teleconnections where things that are far off, something happening in the eastern Pacific, some slight warming could impact temperature and rainfall in South America and Africa. So we are looking at those kind of things, plus the importance of extremes, and these could be recurrent extremes. These are not recurrent in the sense that they happen regularly once every 100 years, so you wait for 100 years and they'll happen, but they are recurrent in terms of a probability distribution. They are likely to happen once every 100 years, and these sometimes cannot be treated as a simple spatiotemporal outlier or an anomaly like they usually do in data mining. So what we have been working towards is a sort of best fit strategy that combines data guided insights with physics based models. And we have at least three ways of thinking about that. One is fairly hypothesis guided analysis in an interpolative sense. So we say that, okay, we know this data set, let us analyze all of this data in the past. Let us analyze model hindcasts, that is models run in the past with observations, see how they behave, extract their statistical properties and see how much we can do. The other is hypothesis guided but more extrapolative analysis, which is saying we are interested in extremes and rare events. Let's say we are interested in 100-year events, but we do not have enough data at those tails for those 100-year events. So if we wait 1,000 years, we might get 10 of those on the average 100-year events, but by that time the climate might change. So question then is, we look at some high values like an annual maxima or like values that are above some threshold. We look at some high values, develop some sort of parameterization schemes which can be thought of as central limit theorem but for extremes, to infer about what happens at the tails for these 100-year distributions. So that's this extrapolative analysis. And then we also look at relatively hypothesis free discovery processes, which is saying that, okay, let's see what we can learn just from data itself, and then based on what we learn, how much of that exists within traditional domain knowledge already, which can be used as validation, and how much, and maybe there's something that's new, and if it's new, does this give us any new inferences, both about the science and about predictive skills. So this is one paper that we published recently in PNAS, which talked about, this is fairly hypothesis guided analysis, which found higher trends but larger uncertainty and geographical variability in temperature and heat waves in the 21st century. And this looked at fairly detailed exploratory type of analysis of the uncertainty. So I've already shown you this, where this looked at model simulations minus observations at decadal scales and found these are Gaussian. This looked at geographical bias, observation minus model, and how they are dispersed regionally. Fairly interesting patterns there, which I'll not go over right now, but fairly interesting patterns with topography, with where you are, and so on and so forth. This looked at difference across scenarios. Scenarios are our future estimates of greenhouse gas emissions. Depending on how we estimate those, the world might look very different, or how we project those, the world might look very different. And that's something that these are more what if scenarios. We don't know what the future greenhouse gas projections will be. So we just do what if it were this versus that, how different would those be, and they would be fairly different. And these are differences across ensembles. Ensemble runs are different runs of the same model with the same forcing or with the same greenhouse gas scenario, but these are run with slightly different initial conditions. And this is done because the climate system is chaotic, meaning it's sensitive to initial conditions. These are done to see how much that affects global to regional scale predictions, and we see that there is some differences there. Yes?
If it quickly forgets the initial condition, then why does the initial condition affect the model run?
Well, the idea is to see if it really does quickly forget the initial condition.
So this seems to suggest that it doesn't.
Right, and that is what chaotic systems usually do, and climate systems are thought to be chaotic. So yes,
Are all of these graphs
it does not forget initial conditions quickly. Yes.
Are all of these graphs on the same color scale? In other words, do they what are they showing as temperature?
Yes, temperature change.
So is the red, say, on the left-hand side, difference across scenarios, is that red the same red as the red that would be in the graphs on the right?
Roughly, except these are absolute temperatures and these are differences.
I see.
Yeah, and these details are there on the paper, but yes, I mean that's a valid point. I mean from a visual sense, it just gives a sense of.
It look like we could just ignore everything and just focus on the question of how much carbon are we going to output? Because that. You know,
Oh no! You are right. No, I'm sorry. This is absolute,
Okay.
and these are differences. So we do need to look at both of them. Yes, that's a good point actually. Okay, so here, when we look at these different scenarios, these are these greenhouse gas emission scenarios. The A1FI, these are just names. A1FI is the fossil fuel intensive scenario. This was considered so extreme or so worst case at some point that some models like CCSM3 did not even run with this scenario earlier. But then some people found that current emissions trends are going or even exceeding A1FI. So then people scrambled to run CCSM3 with A1FI. And then what we try to see is, in a statistically significant way, can we make a distinction between A1FI and A2, which was considered to be one of the worst case earlier. And what we found, and this is based on all of these uncertainty quantification that we have done earlier, except that if you look here, these are fairly steady. These don't change. And of course, these are expected to change as you go in the future. You're going to grow more and more uncertain. These don't change simply because we have fixed them. We do not consider lead time effect. So these can be looked upon as uncertainties due to model sensitivities in the current decade and past decades. Because we have found that these errors are stationary, so we can still use these without lead time effects. So even without that, if you consider these, around middle of this century is when these things become statistically significant. So A1FI, which is the new worst case, becomes worse than A2. The other thing that we noticed is sometimes impacts modelers use these model ensembles as estimates of uncertainty. Model ensembles are run because the climate system is chaotic, so these are different initial conditions. What we found is that this uncertainty, even after ignoring lead time effects, this uncertainty is much larger than these ensemble bounds would appear to suggest. So what you're saying is there is larger uncertainty, but there is a higher trend, even at global scales. And yes?
How do you generate the statistical ensembles?
So the ensembles themselves are generated by running models with different initial conditions and same or different forcing, depending on what you are trying to look at. The uncertainty bounds were generated by us by comparing with observations and looking at the error statistics.
How do you select the initial conditions?
Oh, okay. So I'll not go over that right now because it's a huge topic, but there are ways in which that is done, right? In terms of saying that, okay, let's start with current conditions. Currently, here is what we know. So roughly it will be like this. Here is what we know about the current condition, that temperature is so much, this is so much, this is so much, and here we are is what we know about the statistical distribution around that current condition. Your measurements are never going to be 100% accurate, so maybe you have a statistical distribution. So then you sample from this distribution and run these simulations based on that sample. So this is sample from the distribution of initial conditions. But they might, I mean, if it is a chaotic system, they might not all look similar. So that's the whole point. But there, I mean, I'm sort of, oversimplifying a whole branch of study, but those are there. So in terms of then, when you look at model projections, this is 2050, this is 2100. These are most likely curves or values. These are upper bounds, these are lower bounds. Once again, I'll not go into the details of these, but what they show is that there is significant uncertainty at regional scales. Lower bounds, if you look here, even by 2050 almost hardly show much warming other than in certain regions. however, that warming trend is clearly there, because even this lower bound shows warming by 2100. However, the upper bounds are even worse, than what we thought. So upper bounds in 2050, 2100, that shows significantly more warming than what we thought. So what this means is that the fact that trends are higher than what we thought, but uncertainties and variabilities are also higher, means that the urgency is there to act. At the same time, the complexity of decision making is a little bit harder than what we thought. Same for heat waves. So we define heat waves as consecutive minima events. So 3 nights exceeding certain temperature. That's one way in which heat waves have been defined in the literature. And we found something similar. In fact, what we found there is that if this is that upper bound from A1FI, and observed heat waves are actually even higher than this upper bound, at least for this decade. We don't have enough data there, but based on what little we have, this seems even higher. This is the heat wave intensity, the average intensity of heat waves. And same in terms of regional bounds. And we obtain something similar when we look at frequency and duration. Those also tend to worsen as we go from now to 2050 to 2100. So increased intensity, duration, and frequency of heat waves is what we see, together with their uncertainties. So that was that one thing. Now I'll go over this extrapolative analysis, where we look at extremes in a slightly different way, which is through the statistical approach of extreme value theory. So what we show here, this is 30-year rainfall event right now. Instead of 100-year rainfall, we have used 30-year because that's what could be better supported by the data sets that we have. So this is model hindcast, models run in the past. And what this shows is that what used to be 40-year events earlier have become 30-year events. So that means what would happen once every 40 years, now we expect this to happen once every 30 years. And then these are the different scenarios. And what we see is that this 30-year event becomes almost a 7-year event here, or 5-year. Question then is, how much do we trust these things? One is to test goodness of fit of these models based on, that is just based on estimation from data. We have done that, and that looks fairly well. But the other key thing is, how do these trends agree with observed trends? So we looked at reanalysis data. Reanalysis is basically looking at many different types of observations from different types of sensors and do a meteorologically viable curve fitting on those. So if we look at those, then here is one reanalysis, here is another, and sure, they do follow some of these trends, not exactly, but there is this kind of match. This is visual. We do have some more some other work that supports or not supports some of these things quantitatively. And similarly, we see these kind of things both in observations. These have been reported by other people also, and in simulations. However, once again, look at the discrepancy. So this is ERA 40 and NCEP 1 or 2. These are reanalysis data sets, surrogates of observations generated in slightly different ways. CCSM3 and CSIRO, these are 2 climate models. So we are looking at difference of one versus the other from the period 1970 to 99 for 24-hour, 30-year rainfall extremes. And these are percent differences, negative, positive. Difference is very high in the equatorial regions typically, which is expected. This is observation minus observation. So why is this huge difference? Well, because the way these reanalysis data sets are generated is, it's a reconstruction of past climate based on all the observation that you have, but that reconstruction is done with a meteorological model. So what you have here is that our understanding of that basic meteorology is problematic, especially in the equator. And then you compare models with observations, or reanalysis models with reanalysis, and you have this kind of things for extremes. So plenty of scope for improvement, a lot of uncertainties remaining. Similarly, when we look at two different reanalysis data sets and see what kind of rainfall mechanism generated these extremes, these design storms. So is it at a very fundamental level, is it convective rainfall? Convective is when the land grows warm, the parcel of air rises, and you have the water that was there in that parcel falls down as rain, versus is it caused by frontal effects, meaning very large wind patterns moving from one part of the world to another and hence potentially causing rainfall. These are two big, very different kinds of mechanisms. If we look at this, if we look at rainfall extremes in this way, 6-hour annual maximum in this case, the two reanalysis data sets show significant difference. And this is reanalysis. So this difference is just because of our understanding of the meteorology within this reanalysis. This is the percentage of that extreme rainfall generated through convective activity. The model seems to lie somewhere exactly in between. So that's interesting. How do you interpret that? On the other hand, at global scale, when you look at some of the physics, this physics is called Clausius-Clapeyron. What this means is that warmer air or warmer atmospheric column has greater capacity to hold water. When you look at that, that physics seems to hold up both from models and from observations, and there is this the increased intensity and frequency of precipitation extremes seem to be supported by both. And these can be translated to in what are called intensity duration frequency curves, which are used by civil engineers, water resources planners for their design. So intensity duration frequency curves are used for design of urban drainage systems, sewer systems, hydraulic engineering infrastructures, etc., etc. So that's one. However, the moment we get from these global scales to regional scales, I'm not showing them here, we inherit a lot of uncertainty just through that when you look at this process. Finally, I'm just going to quickly touch on relatively hypothesis-free discovery. This is the data-guided hypothesis I was talking about. When you're talking about looking at ocean predictions, trying to see if they can improve predictions of climate extremes, we try to learn this relation from data and then use that to refine climate model outputs. This part we haven't done yet. We're just looking at this now. So we looked at complex networks as one way to do that, and what we found from these complex networks, without going into them too much, is that there is, in most cases, when we looked at different types of oceanic variables like sea surface temperature, sea level pressure, precipitable water, etc., we found mostly what you'd expect. Sea surface temperature, for example, has significant amount of proximity-based spatial correlation and something in the tail, which means there are some teleconnections. In the lingo of complex networks, it would be called a small world property. Precipitable water has proximity-based correlations. When we look at updraft velocity, which is a measure of convective patterns, we found something interesting. There is relatively no proximity-based correlation, which is what you'd expect. Convection is supposed to be very hard to model, and it has a short correlation scale in space. However, we do find these tails, and we're not sure yet here if these tails, if this is just spurious correlation or if this is some evidence of long-range spatial activity. So one thing we did is we looked at all of these different variables, translated these into predictors, these clusters. These are clusters obtained from complex networks through community identification techniques, and then we use these as predictors to see what kind of value we obtain for prediction over land, for, in this case, for temperature and precipitation anomalies over land. And one thing that we did also is that we said, well, let's look at, once we predict these, let's take a look at those again and see which of those predictors we would have used just from a domain or from a climate.
Placing pressure on the output side, and this is under forward flow. You pop these flaps up, but this remains closed, and fluid comes out. And this is a way to make a check valve, I should mention, that is integrated with a channel on a surface, as opposed to the other examples I showed you where they kind of go from the bottom to the top of a chip. And this kind of shows that it in fact works. All right, so I think we're out of time on, okay, perfect, out of time on the video, so this is a good place to stop. Are there any questions?